Okay, we're going to start chapter 6 and we're going to do 6.1 today, which is graphing a system of equations. Anytime you have to graph a system, we're talking about more than one equation, linear equation that you have to graph on the same graph. So let's look at the warm-up first. Alexis calculates the surface area of a gift box as 600 square inches. The actual surface area, this is Alexis's surface area is 600 square inches. The actual surface area is 592 square inches. They want us to find the relative error of Alexis's calculation expressed as a decimal to the nearest thousandth. Okay, so relative error. This is review. Remember, relative error is human error. So what percent or fraction or decimal of human error did Alexis make in the actual measurements? So subtract off the 2, 600 and minus 592, and always divide by the actual, which in this case is 592. 600 minus 592 is equal to 8. And then you're going to divide that by 592, which is equal to 0.135135. It keeps going. Okay, that's why they're telling us to round it off to nearest thousandth, which is 10th, 100th, thousandth, which is this place. So therefore, the relative error is about, and they want it as a decimal. So most of the time they ask you to change it to a percent, but in this case it's a decimal. So it's 0.135, which is about 13.5%, which is a little bit high for human error. Solving systems by graphing. This is 6.1. When you're given two equations, when you have two different variables involved, typically an x and a y, but it doesn't necessarily have to be that, and you're asked to solve the system, because there's two of them, you can do this two different ways. You can do it graphically, which works only sometimes because where the actual answer comes out, it may be a decimal, which is not easy to read on a graph, so we say it works only sometimes. And algebraically, which will always work, and there's two different algebraic methods you guys are going to learn, which is substitution and elimination, but we're not going to do that today. We are going to focus on graphically. Solving it graphically, here's the process. I'm trying to break it down into steps. Graph each equation on the same graph by using any linear form that you have learned, whether it's y equals mx plus b, whether it's building a table, whether it's the point slope form, picking out the point and the slope and graphing it. Make sure that you graph it on the same graph though. Circle the point of intersection wherever the two lines intersect, which will be 90% of the time. Circle that point of intersection because that's actually your solution. And then take that solution and do the two checks. Why two checks? Because there are two equations and there's a check per equation that you have to do, which means you're going to substitute the point into each equation to check. Now, going back to step 2, circling the point of intersection, does it mean that whenever you graph two lines they will always intersect? No. Most of the time they're going to intersect, but there is a time where they may not intersect. That's where the two lines end up being parallel. So there are three different types of answers, and this kind of summarizes it before we actually do a problem. If you graph your two lines and they actually intersect, which in this case would be at this point, which is -1, 1, so the solution in this would be -1, and there is one solution. If your two lines, when you graph them, end up being one on top of the other, so they're exactly the same line, that means that every point on that line actually is an intersecting point for those two lines. And how many points are there on a line? There is an infinite number of solutions. The third scenario is where the two lines that you graph end up becoming parallel. Their slopes are equal, they're parallel lines, which means that the two lines will actually never intersect. And if they never intersect, then there is no solution. 90% of the time, you're going to end up with this situation, one solution. So you are going to have to do the checks. If you end up with infinite solutions or no solution, those are the times when you don't do the checks. All right, let's look at an example. Solve the system of equations graphically. So we have two equations. Nicely enough, they've started us off with two equations that are in slope-intercept form. Y equals mx plus b. So the m in the first equation is equal to 1 over 1, and the y-intercept is equal to 2. In the second equation, the m is equal to 3 over 1, and the y-intercept is equal to negative 2. So now we have enough information to graph both of these lines. We're going to graph these on the same graph and find out if they intersect, and if they do, then we'll pick our point of solution. So get a piece of graph paper. If you have to put me on pause, that's fine. And let's go ahead and graph. Don't forget, you got to have, everything's got to be labeled, your x, y axes. Notice how they put the x on the left and the y on the bottom, which is totally okay. And let's go ahead and graph our first equation. The first equation had a y-intercept of 2. So that means you're going to start at 2 on the y-axis, and the slope was 1 over 1. So it's going to go up 1 to the right 1, up 1 to the right 1, up 1 to the right 1, or down 1 to the left 1, down 1 to the left 1, down 1 to the left 1. Go ahead and take your straight edge and connect those points with a line. Make sure you try to extend that line all the way through the graph, because your intersecting point may actually be way down or way above or way up on that line. So make sure that you show both all the way through the graph. Don't forget to label it. The equation was y equals x plus 2. So let's go ahead and label it nice and neat, y equals x plus 2. And don't forget to label your graph. The second equation is y equals 3x minus 2. Slope intercept, or points, or slope, y-intercepts at negative 2, which is right here, and the slope is negative or positive 3, so it's up 3. 1, 2, 3 to the right 1. 1, 2, 3 to the right 1. There's our intersecting point. 1, 2, 3 to the right 1. 1, 2, 3 to the right 1. Go ahead and grab your straight edge, and let's connect it with a line. Make sure you go all the way through, and don't forget to label it, the equation of the line, which is y is equal to 3x minus 2. Now, here's the part that you have to be careful with. Circle the point of intersection, which I did, and the solution is that point where they intersected, which is 2, 4. So that's actually the answer to the system of equations. Remember, system just means it's because I've graphed two equations. So now I'm going to have to go ahead and do two checks. So I'm going to do my two checks up here. First, I'm going to substitute my 2 in for my x and my 4 in for my y into my y equals x plus 2. So check number 1. Y equals x plus 2. Substituting 4 in for my y, my 2 in for my x plus 2, and 2 plus 2 is equal to 4, so therefore it checks. My second check and they both have to check. If one checks and the other doesn't, that means it actually doesn't work and we have a mistake somewhere. So they have to check in both equations. Let's go ahead and substitute the 2 and the 4 into my second equation. That would be 4 is equal to 3 times 2 minus 2. 4 is equal to 6 minus 2. And 4 is equal to 4. 6 minus 2 is 4. So it checks. So my solution 2, 4 is the solution to this system of equations. All right, we have a, let me see here, whoops. We have another graph here. This is a word problem. It's kind of hard to read. I'll translate it over for you. It says, scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth of each alligator are shown below. After how many months did the alligators weigh the same amount? So in other words, you're actually going to set them equal here. So let's look at this. Alligator number 1, the initial weight for alligator number 1 was equal to 4 pounds. And then the rate of growth, which really is my slope, is equal to 1.5 pounds per month. Now 1.5 is equal to 1.5, which is equal to 2 times 1 is 2, and 2 plus 1 is 3 over 2, changing a mixed number to an improper. So my equation for my alligator number 1 would be, and I'm going to use y and x for the sake of an xy axis on a graph, it's equal to the change of growth per month is 1.5, which I'm going to use my 3/2 because I like my slope as a fraction, times x plus, it started at 4 pounds, so we've got to add 4 pounds. Now, alligator number 2, starting weight was 6 pounds, and its rate of growth, which is the slope, is equal to 1, which is 1 over 1. So that equation is going to be y is equal to the slope, which is 1, x plus 6. I don't really need my 1 here, but my slope in the first one is 3 over 2. My y-intercept is 4. My second alligator has a slope or rate of growth of 1 over 1 with a y-intercept or starting weight at 6 pounds. So go ahead and get your graph ready, and let's see where these two lines intersect to see when they actually weighed the same amount. Oops, I didn't want to do that. Alright, so set up your XY axes. Make sure you put arrows on the end, and let's go ahead and graph these. The problem with this, nope, there's no problems. We have starting on the y-axis at 4, and then the slope is 3 over 2. So start at 4, and then go up 1, 2, 3, 1, 2. Growth of 1, 2, 3, 1, 2. Or we can go down 3 to the left 2. Down 3 to the left 2. Connect that with a line. And then label it, which was y equals 3/2 x plus 4. That represents alligator number 1. Then we have alligator number 2. Alligator number 2 started at 6 pounds and had a rate of growth of 1. So 6 pounds and a rate of growth of 1. Up 1 to the right 1, 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 or down 1 to the left 1. Connect that with a line. Looks like they're intersecting. It's kind of hard to see with my graph, but 1, 2, 3, 1, 2. Looks like they're intersecting at this point right here. Just check this. 3